Hello everyone. So today I'll be taking us on the step-by-step process of how I was able to validate this particular problem on ANSYS software. That's a steady-state thermal using steady-state thermal analysis. Since I'll be getting a lot of requests on my LinkedIn page on showing them step-by-step process of how I'm able to validate the results. So this is another particular problem that is already solved in the same textbook. So we just want to see similar results on ANSYS or if there's any little differences. So this project or this particular problem, the aim of this problem is to find the maximum temperature in the system and likewise the outer surface temperature of the two slabs. So these are the two slabs here. You can still go back to this question and read through, but I'll be explaining more on the ANSYS software. Now we are on the ANSYS environment, and what you are seeing here is a folder or a tree which I've worked on to validate the results, but we'll be starting from afresh. So you just have to go straight down to your left hand side and look for this particular tree or folder called steady-state thermal, because majorly of what we are doing, the problem we are solving is thermal analysis that has to do with conduction. So you go straight down and look for it. This is steady-state thermal analysis. You drag it, then put it onto your workspace here. So it will take a while to load. So we have it here. So the first step you need to go is to ensure you have to go to this engineering data. This engineering data is one that comprises of the materials of the composite or the machine or the model you want to analyze. Let's go back to the question. When you go back to the question, you notice that it was stated there that the slab A has a particular property, which is the thermal conductivity K, which is 50 watts per meter Celsius, and likewise our slab B, it is given as 0.2 watts per meter Celsius. So you need to take note of this. That is the only information given to us, and for the heater there is not any particular information given to us. So you can use any thermal materials that can actually generate it for us. So you need to pay attention. That is the first thing you need to pay attention on, the properties and likewise the dimension. But since we are talking about the materials first, we just need to first consider the properties. So right now, back to our workspace. So what I just need to do here is, since I have actually worked on it, I'll just drag this engineering data, drag it to this place. So automatically it will have the same information, but I'll still need to open it and show you the properties. So here these are my properties that I already established: the slab A, the slab B, the stainless steel, and copper. So I just have to put stainless steel in case my copper doesn't work. So when you click on slab A, you see that it's only isotopic thermal conductivity information that is there, and because that's the only information I was given, which is 50, and slab B, it is 0.2 from the question, and our heat source, which is either be copper or stainless steel, anyone that works for you. So far you are getting the same or similar results from the textbook. So this is how I was able to establish my material. Then next we'll go to the model. So back to our workspace, we want to design. So what we come here and start with drawing, what I just need to do is to come to the one I've drew already, right click, then go to edit geometry in design modeler, because this is what I use, which is more easier and understandable, friendly than the space claim. To me, it's more friendly than space claim. So I'll go to design modeler. It take like 2 or 3 or 5 seconds right now. So this is my model, designed dimensions as what is given from the textbook. So if you pay attention, you'll see that from the textbook it is stated that a square plate heater 15 centimeter by 15 centimeter is inserted between two slabs. So, and once you look at this diagram, you notice it's not a square plate, it's looking like a rectangle. So what does it mean? It means that this is a 3D model, but it's represented by 2D. That means there's another elongation at the other view or the other side that is 15 centimeter long, both the slabs and the heater. But here, which is the thickness of the slab, which is 2 centimeter and 1 centimeter, but the thickness of the heater was not given. So you just need to just improvise by giving it a value less than 1 centimeter, not something greater than it. So that's how we can able to achieve this particular one. So all these are dimension with respect to what is given from the textbook. It has to be like that so that we get the right answer. So once you check it, for example, this model here, so this my V1, this is the vertical line V1. It is, when you look at my left hand side here, V1, it is 50 centimeter, and H2, which is down. When I click on it, it will show this H2, which is the base, which is the sum of the slab A thickness and slab B thickness, which is 2 centimeter plus 1 centimeter, and my assumed value for the eta, which is 0.8 that I use to get this 3.8 centimeter. So all these are what I use to get my model. And if you notice from my left hand side, you see face lips and bond surface shape this particular, because you know from the shape or from the 2D drawing you see that it has 3 different surfaces. So and to achieve that on ANSYS, you need to like firstly create a surface. You go to the concept, you go to this concept here, you click on concept, and you see surface from sketch. So from my rectangle shape which I first draw, I'll create a shape, a surface from it. Then after you get the surface, then you have to split the surface into the numbers of surfaces you want to get. So I draw this, that way you see the second sketch. So this second sketch, I just comprised of these two lines which I drew, and then I went to this tooth. Is this tooth, I was able to see this face splits, that I was able to split the surface into two faces. That's phase one and phase two. You can see phase one, phase two. Then I use this discharge tool from the concept. You see the word discharge here, so it's automatically like discharge the surface. Then you will now have like 3 surface body, because this surface body are what we are going to use in the next step, where we are going to be assigning the material, because this one here will stand as slab A, this will stand as slab B, and this will be for the eta. The next phase is to move to the model. So I'll click on the model and start editing. Since we've actually assigned the materials that we need, we've drawn the model to dimension, and we split the faces into 3 surfaces so that we can assign the materials selected here. We can put it there. So the next is the model. It will take like 5 seconds or 10 seconds, 5 to 10 seconds. Guys, so we are on the final phase, which is also the main and the important phase. All steps are important too, but this is where we will get our final answer, and if we should miss it here, we might not really get the answer, because there are major steps here that we need to consider. So firstly, when you come to this particular place, you have to first go through your geometry, look at your geometry to ensure if it's what we want. So you see that from what we did, we have 3 surfaces here. When I click on the surface body, it will show you the color here in your workspace. So the surface body here, that means that's slab B. You can also like edit the name so that it won't get you confused. But since I can click on it and it will be showing me here, then I don't need to worry about editing the name. So the next one is also slab A. That means the last one is the eta here. So and we can see when I click on this surface body, you have to also come down here and check the materials it is assigned to. So this is where you will assign the materials you have built up from the engineering data. So now that means that this eta body, I'm using copper as my eta body to provide or to produce it into this model. And then this slab B, I also put it there as what, slab B. And you notice in my thickness, I put the 0.15 meter, which is 15 centimeter. So you need to note those dimensions. And likewise for the last one, which is slab A, so that and slab A, the materials is assigned to it. So that one is the first phase in this model workspace. Then the next one you need to go is your mesh. Your mesh is very important. So what I use when I generate my mesh, I use 0.003, sorry, 0.001, and this is what I can get. So it's showing me, I can from here I can see that it's a nice mesh. It's a nice mesh. From here you can see that it is uniform and it's giving me what I want. So you just need to ensure that you get a smooth and fine mesh, because it is very important in your analysis. Yeah, so the next one is to move into the initial condition and the bounding conditions. After you've gotten your fine mesh, let's go to the question and see what is written in the question. So from the question, you can notice it said here that the slab A, has a thermal conductivity, which is the materials, and from there, say the outside heat transfer coefficient of side A, or you can also call it slab A, and side B or slab B are 200 watts per meter square Celsius, and likewise for slab B it is 50 watts per meter square Celsius. So this is what they call convection. This is convection when you are trying to interpret it with ANSYS, or that steady state thermal analysis. So when you have to right click from here, then you choose your conversion here. So you can see my boundary conditions. When I click on this thermal, this one here, you can see all the boundary condition I use. The conversion here, which is you can see from my information here, the conversion here is what I use. I mean, this side, this edge of the slab A or the side A is where I use it. Considering from what it is written in the question, it says side A, so I just have to go straight and use the edge. That's why you see that my geometric, I use the edge, and I provide all the information given from the textbook. Then the conversion 2 is for the other side of the side B, and all informations are also given. And now the next one we need to also consider is this third one, which is internal heat generation, which I have to explain very well for us to understand. From the question, I always refer back to the question. From the question, there's nothing here that you see internal heat generation, and that is why you need to be extraordinarily careful. Now you notice in this question here, we were given the square plate heater, which is 15 cm by 15 cm, right? And we are also given the rating of the heater, which is 1 kilowatts, right? So this is what you are going to be using to get your heat generation. And once you look at the way it was solved, you can notice that they actually use the formula to get our answer. So how can we achieve that on ANSYS? So what we need to do is we still need to do a little calculation on how we can get this for answer. So what I did was I did a rough calculation, because my internal heat generation, the formula for internal heat generation is the kilowatt, I mean the heat generated divided by the volume. And what is my volume? My volume is area times thickness. And what is my area? Area is the 15 by 15 cm, and the thickness is what I use. Sorry, the thickness is what I use for this particular length here at this base, which is 0.08. So once you multiply 0.08 times the area given to us, that's 15 by 15, you will get this particular value. So that is what you will use, because let me state it again. Internal heat generation, that's Q, is equals to the heat flow divided by the volume. So once you can do that, you'll be able to get this particular value. Then you come to this internal heat generation, then insert your value to it. So once it is inputted, that means all informations, all values have been used. Then you can now like solve it. So when you want to solve it, from the question, it said we should find the maximum temperature. Let me go back to the question again. They find the maximum temperature in the system, and also the outer surface temperature of the two slabs, which is this at my left hand side and the other edge at my right hand side. These are the solutions to our simulations we did, and we'll be comparing it with the solved problem. For instance, this temperature, which is the maximum temperature for the probe, if you can zoom, you can see the rate at which the heat is being transferred from the authored region. And what we are having here, the maximum is 248.35. So we have to compare it with the soft problem. I'm going to be checking. So here we can see from the question, you see 247.8 degrees Celsius, and from our analysis, I'm getting 248.35, right? So which shows now we are having similar results. So this is just 247.8 degrees, approximately 248, and we are having 248.35, and that's just a little numerical error based on our mesh. So define the mesh, define you start getting accurate results. So that is for the maximum temperature, and likewise for the temperature probe, which is for the one at the side A. What we are having here, you can see that is around side A. We are having two we have been to 31.45 degrees Celsius, which is our temperature here. Just take note, 231.45 degree. And from our calculation here too, we can get our T1, this T mass, and from the calculation T1, we can get it to 31.31 degrees Celsius, which really matches well with our results. So, and for the last one, which is probe 2, which is at the right hand side, I'm getting 88.8193, approximately 89. And from here to, I'm getting 88.6, which is approximately 89 degree. So guys, this is how I'm able to validate both the soft problem that is solved on the textbook with ANSYS software. Thank you guys.